All right, welcome to part 2 of elimination and back substitution. In the first video, we identified that when we want to solve for a system, we want to solve it using elimination. And we saw in the 2x2 case that works very similar to Algebra 1 and Algebra 2 and what we've learned in terms of high school mathematics. Once we start getting into 3x3s, even though that's still kind of Algebra 2, the process applies to any dimension square matrix that we have. And one of the important things that we will discuss at the very end of this video is when we're transforming into an upper triangular matrix, that upper triangular matrix tells us so much information about the original matrix A and really about our system in terms of what we're solving for. So when I'm looking at my matrix A, again, this video's purpose is to walk you through what that elimination looks like and using matrix multiplication for that. I first want to identify that this entry here, this is the A11 entry, row 1, column 1, is a non-zero number. So that means this is my first pivot and row 1 is locked. We don't need to do any work with my first row. So we're actually going to leave that there. What we want to do to transform this into an upper triangular matrix is I want to zero out every entry below that pivot point. Remember that upper triangular matrices are defined as containing zeros below this main diagonal. That means once I identify my pivot points in A11, A22, and A33, I should have zeros underneath those pivot points. So even if this added another row and column to make this a 4x4, the idea is still the same. Zero out every entry below 2, zero out every entry below A22, zero out below A33, and then A44 would be my final pivot point in that matrix. And so that's the strategy and that's the idea. So it's an easy extension as we get further into higher dimensions in terms of the square matrix. Now, how we eliminate that is going to be very similar to what we've seen in Unit 1 and elimination idea if these were flat out equations. The idea is that I want to take this row and I want to add or subtract a combination of the first row, essentially doing a replacement. Now, when I do that type of replacement, because we're working with the rows, I'm going to multiply my matrix A on the left by what's referred to as an elementary matrix IJ. IJ is referring to the row and column entry that I'm trying to ultimately replace or change or eliminate. E can stand for elementary matrix. You can also stand for elimination matrix if you would like to. But it is built off of using the identity matrix and changing the identity matrix in the spot that I ultimately want to get rid of and alter. So for example, if I'm trying to eliminate this 4 that is in the 2, 1 spot, then I'm going to multiply by E21. And because I want to eliminate that 4, I need to multiply the first row by -2. I'm going to replace the spot in 2, 1 with -2. So I'm just double checking. Yep. So I got distracted by my notes on the side. So what happens then is if I perform the matrix multiplication, if I do E21 times A, so I'm going to put A here on the side, 2, 3, 4, 4, 11, 14, 2, 8, 17. When I perform this multiplication, because we're essentially going row by column, because this is 1, 0, 0, notice how that keeps this first row the same. That's that identity piece of multiplying on the left-hand side. 1 times 2, 0 times 4, 0 times 2, and this runs all the way down the line, so my first row remains unchanged. Also notice, because this third row times each column is 0, 0, 1, 0, 0, 1, 0, 0, 1, the third row also remains unchanged. This is important because remember, I'm only trying to eliminate this 4, which will ultimately change only the second row. We want everything else to remain the same. When I go through and now work with the second row, notice how this will take -2 times the first row and add that to each entry in the second row. Nothing multiplies with the third, so there's no third combination. We're only ever working with 2 rows at a time. So I have -2 times 2, which is -4, plus 4 is 0. And we've accomplished the 0 entry there in A21. Now if I do negative 2 times 3, that gives me negative 6, plus 11 gives me 5. Negative 2 times 4 is negative 8, plus 14 gives me 6. And thus I have my first transformation there on the left-hand side. Now, what we have to remember is that if I'm multiplying on the left by something, we need to multiply b on the left-hand side by that same elementary matrix. So as we affect one side, we need to affect the other. So I'm going to perform this combination, negative 2, 1, 0, 0, 0, 1, on b. And this is how b gets transformed into that c vector. And we do this for every computation and combination. So 19, 55, and 50. To cheat a little bit, this result comes out to be 19, 17, and 50. Again, the second entry is the one that gets affected because it's the second row that is affecting in terms of these columns. Negative 2 times 19 plus 55. And so I have our first elementary operation, elementary in terms of eliminating. And so we have here, we can call this A1, whatever you want to look at, but this is my next step here. Well, looking at this matrix, we need to zero out this 2 entry here. Again, this is my pivot point. We need zeros underneath to make this into an upper triangular matrix. So now, notice how I need to multiply the first row by negative 1, and then add it with the third row. That will eliminate this entry. Also will affect these other entries, but the second row now will go unchanged. So to perform that, I erase what I have, right here at least. I'm going to eliminate third row, first column. We're multiplying that with E21 times A, because that was my first step. So we have this matrix that we're trying to figure out. We're multiplying 2, 3, 4, 0, 5, 6, 2, 8, and 17 by it. I'm trying to figure out what this will now be. I can just erase that third row. Well, the first row is staying the same, so 1, 0, 0. The second row is staying the same, so 0, 1, 0. It is here, remember, that I'm taking the first row and adding it, with the third. So we replace the 3, 1 entry with negative 1. And then now in terms of doing that multiplication, I know things will cancel out. When I go through and perform that operation, those will create a 0, which is our objective. 8 minus 3 is 5. 17 minus 4 is 13. And then remember that whatever I multiply here, we need to multiply here as well. So I'm going to take that 19, and actually I'll just leave this 1, 0, 0, 0, 1, 0, negative 1, 0, 1. We're going to multiply 19, 17, 50 by that same elementary matrix. And if I do that, we get the new 19, 17, and 31. Once I've located that first pivot in that A11 spot, once we then have zeroed out every entry below that, we move now to the next pivot along the diagonal. And my check is this second entry 0 or not? If it is not 0, then we are good to proceed. And the idea now is we want to multiply by an elementary matrix that will eliminate this entry below. Essentially notice that as A32. We can see that elimination pretty quickly, which we'll perform in a minute. But the question then kind of arises, well, what if that is 0? Then what does that mean? And we're going to talk about that implication at the end. But just know that right now we're still in the clear. It's perfect. And so we're going to go through now. I have 2, 5. Remember, that was the pivot from the last video. We want to eliminate that entry there. So we want to multiply by another matrix. This time, again, we're eliminating 3, 2. So that means in terms of what I'm multiplying by, this is going to be a negative 1 in the 3, 2 spot because we're just multiplying the second row by negative 1 and adding it with the third. So I'm going to rewrite here 0, 5, and 13 because the first 2 rows stay the same. And that means here I can just go ahead and do my elimination. 5 minus 5 is 0. 13 minus 6 is 7. And remember, this was our final pivot point because it's our last entry in the main diagonal. If I come over here and I multiply by the same thing, E3, 2, this would be 0 and negative 1, 19, 17, and 31. It's the third entry that's getting changed, and it gets altered into what we had for C, which was 14. Notice that my result now, after multiplying by these L3 elementary or elimination matrices, we get an upper triangular matrix. This is my U. How we transform B by multiplying on the left by those same exact matrices is my C. And solving this system, because we've done elementary operations, we haven't changed the system, we've just changed what it looks like. And now the solutions to this system are the solutions to the original problem. And this is the same upper triangular system that we solved in the previous video. And this kind of shows you and walks you through how that upper triangular matrix was found and how it was created. But now we have our solution. X is equal to 4, 1, 2. We have a singular solution. Because we have a singular solution, exactly 1, then that means that my matrix A had full rank. It had 3 independent columns. Very, very important to know. So the question then comes back. So if we look back here at this problem, and again, once we got to the second entry, so essentially right here, and we said, okay, well, this pivot point was a non-zero number. The question is like, is there a breakdown of elimination if this came out to be 0? And so he gives a example. I'll pull it up so I can make sure I see. So suppose we had a new matrix A. So we're just going to focus on the matrix. We're not going to worry about my B. And let's say my new matrix for A was 2, 3, 4. 4, this entry was now 6, 14, and then 2, 8, 17. So everything stayed the same except for that one middle entry. Now if I follow through the same elimination procedure, we want to eliminate these zeros here. The matrices that we would multiply by are the same. E21 is still the same matrix as before because we didn't change those column entries. So it would still be 1, 0, 0, 2, 1, so negative 2, 1, 0, 0, 0, 1. I would still multiply by E31, because again, we're still eliminating that 2, so 1, 0, 0, 0, 1, 0, negative 1, 0, 1. It is after we do this elimination procedure that if I apply this in the order that we did before, my result would look something like this. The first row would remain the same. I would have zeros underneath that first pivot. But the second row would be 0, 0, 6. The third row is 0, 5, 13. And I want you to notice that we have our first pivot here, but when I go to my A22 spot, we have a 0 pivot, and we can't have that when we're trying to solve the system. But notice that in the third equation, we have a possible pivot point that is not a 0 if we swap rows. And so what we call that is a permutation. When we look at a system of equations, you are allowed to swap equations in their order, because whether I write equation 1, 2, 3, or 2, 1, 3, the solutions are still the same because we're not affecting any of the coefficients. We're just changing the order that they appear in. Well, we can do the same thing when it comes to matrices. If these just represent 3 equations and 3 unknowns, it doesn't matter the order that the rows are in. The solution set should still be the same. We're not changing the true value of what's going on. We're just changing what it looks like. To perform that permutation, and because we're just swapping rows, we've actually seen this already, I can multiply by a matrix P that is essentially the identity matrix where I swap the 2 rows in the identity matrix that I want to see reflected in the matrix. So if I call this matrix B, just a capital B, if I multiply P times B, this is going to swap those 2 rows. And so it kind of corrects this issue of a 0 pivot, because now, let's see, 0, 5, 13, 0, 0, 6, I have a non-zero pivot, non-zero pivot, non-zero pivot, and this matrix is already in upper triangular form. So by multiplying by these 2 and then multiplying by the permutation, we're now in upper triangular form, and we can perform the same thing on the other side to solve the problem. We can swap rows. So the following question, I think the next logical question was, well, what happens if this 6 was also a 0? What happens if swapping the rows doesn't give me a pivot in the second entry, whether that's a 0 or whether that's a 0. So if I went through and did my elimination and there was no way to swap it and create a pivot there, then what that's identifying to you is a new upper triangular matrix, which Dr. Strong uses an asterisk for a scenario like this. And I'm pretty sure he gives an example of this where it doesn't matter, so you can see that in the textbook. Although we still create an upper triangular matrix, one of our variables is a free parameter. In other words, it's telling you that you have dependent columns, and we saw this in the last chapter as well. This is where it kind of comes back, right? Everything kind of spirals back and forth, and we see it interwoven. When this occurs, it's telling you that your original matrix A doesn't have a full rank. So it wouldn't be a rank of 3 if I rewrote this matrix that would change into this one, this U star. It would have essentially infinitely many solutions in terms of those free parameters. It could potentially have no solution depending on what B is, but there's no longer one single solution because it's not full rank. And that's kind of the takeaway ultimately by the end of this, is that when I go through and I convert my matrix to be upper triangular, the pivots identify whether we have independent columns or dependent columns. If I have a non-zero pivot along my main diagonal for each entry, all of my columns are independent, and it means my original matrix has full rank. If there's no way to reorder, and I have a 0 and a pivot spot for my square matrix, then that's telling me I'm not full rank, that I have dependent columns in that matrix, and that leads us to either infinitely many solutions or no solutions. There is a ton of power in this. We will work some more examples in our last video, just so you can see how this interacts a little bit more. And looking in terms of the elementary matrices or the elimination matrices, it is very similar to the elementary row operations that I was discussing in 1.4. So you can also look back at that if you would like to see that in terms of language.